Tonight's speaker is Dr. Thomas Greene. He's an astrophysicist at the Space Science and Astrobiology Division at NASA Ames Research Center. He received his PhD in astronomy from the University of Arizona, which, by the way, is a great department. I'm a big fan of you guys. At NASA Ames, he conducts observational studies of exoplanets and young stars and develops astronomical technologies and instrumentation. He is the co-investigator on the NIRCam and the MIRI science instruments of the JWST. And I think he told us tonight he's been working on this for about 25 years, 27 years, Tom, did I get that right? Can you imagine?
Almost 25.
Imagine how he felt watching the launch. I don't know how you can retain your sanity at a time like that. He also serves on the JWST Users Committee, which means, Tom, that you're going to be simultaneously very popular and a very unpopular man in certain quarters, if you know what I mean. While at NASA Ames, he's also served as the director of the Ames Center for Exoplanet Studies. He's been the project scientist of the Sophia mission, and he's been chief of the astrophysics branch. So as you can see, we're very, very lucky to have him. And so without any further ado, tonight's speaker, Dr. Thomas Greene.
Great. Thank you, Dave. And thank you, Rich, and everybody attending. I always love talking to amateurs. Really happy to talk to you tonight about James Webb. And I've happy to be back talking to the East Bay Astronomical Society. It's been quite a while. I think about 15 years ago, I gave another talk to you folks in Chabot, and that was a lot of fun on another topic. So tonight is James Webb. Thought I'd say a few words first about why we put telescopes in space. So the US has been putting telescopes in space since the 70s. There have been also other countries as well. And it's very appealing because, well, the sky is darker, particularly at the infrared, and we can see more light than we can get through the atmosphere, ultraviolet and whatnot. There's also more nighttime, particularly if we're not interrupted by day-night in orbits. There was a series of great observatories that was launched. There's one here, X-ray facility that is not here, over about 15 years. It was called the Great Observatories that were very panchromatic. There was the Spitzer Space Telescope in the bottom that looked in the infrared. It was launched in 2003, recently decommissioned. Chandra is still going strong with X-rays. And as we know, Hubble is still going strong with mostly visible, a little bit in the ultraviolet and the infrared, launched in 1990, operating for over 30 years now. So James Webb looks mostly in the infrared, so I thought it would be good to talk a little bit about why. Well, the bottom line is because we can see more than we can in visible light. So these are visible light images. Here we've got some meerkats and a crocodile in visible light. And then in infrared, we can see things inside. So the meerkats are warm, right? So they produce infrared radiation, which is heat. And we can get some information that you can't just from the reflected visible light. Interestingly, the crocodile here is very faint, very dim, because it had been in a pool of cool water. And it's a cold-blooded animal. And so its body temperature was consistent with its environment, its recent environment being in cold water. So we can get ideas about temperatures in the infrared. This shows what we're talking about graphically in terms of the spectrum here. So this is quite a range in wavelength range, over a factor of 10 billion from gamma rays out to radio waves. Our eyes only see about a factor of 2 in wavelength, right? It's from the blue cutoff in the near ultraviolet into red. So maybe from like 380 nanometers to 750 or something like that. So, one of the redder things we can see is H alpha, right? And a number of you, I'm sure, have been imaging in it, like 656 nanometers. Hubble sees all that, and it sees considerably into the ultraviolet. It'll see down to below, I think, 100 nanometers or so. There's some important lines there in the ultraviolet, and it sees in the infrared out to about 1.8 microns. So that's about 2 or 3 times longer than what the eye can see. So that's a micron is 1,000 nanometers, just to give you that idea. And Webb will be able to see from green visible light from about 600 nanometers out to 28 microns. So from 0.6 to 28 microns, that's about a factor of 50. It's a huge wavelength range. And Spitzer, we see here, this infrared telescope saw from something like 4 microns out to hundreds of microns, but it was pretty small. It was about a factor of 50 smaller than James Webb. Oh, I see. I've got the wavelength ranges down there. So this shows, if we look into different an astronomical scene, what we can see in different wavelengths of light. This is, you all know, the Eagle Nebula, right, which is M16. There are massive stars forming here. These are young stars, and here we still have remnant dust out of which the stars form. There is still gas collapsing in these fingers, right, in these pillars, and stars are forming. If you look in the near infrared with Hubble, you see that there are some stars here, like this one here is invisible in the visible light, and but it is a bright near infrared young star that's forming. So if you really want to see where things are forming, like this one too is sort of at the tip of this finger of dust, it's just sending a little bit of light out here, visible light. But if you really want to see, you need to look in the infrared. And if you go to far enough infrared wavelengths, I think these are polycyclic aromatic hydrocarbon emission that's being excited and emitting in the infrared, the whole cloud glows, and the whole cloud is warm. So there is much information there. Both you can see through dust and it emits itself. This is a demonstration of an infrared dark cloud. This is, I think, taken with Spitzer. So visible light now, and there's a protostar, a very young star in the middle here, and it has a bipolar jet. So there's a jet coming out towards us, which you see in the bottom, and there's one going away from us. And you have to look in the infrared to see the one going away from us, because otherwise the cloud obscures it. So you really need to, if you want to study young stars forming in dust, you need to look in the infrared, or if you want to see things behind dust clouds. This is a galaxy, so should be familiar, right? This is M51, visible image and infrared image. One interesting thing is if you look where it's faint, where it's dark and visible light, it's bright in the infrared. So where there are dust lanes in galaxies, that's where we have these clouds of dust where young stars form. So we see that there are all these bright young stars in this dust lane that is dark and visible, bright in the infrared. So putting both wavelengths together really gives you a much more complete picture of what's going on in a lot of astrophysical scenarios. So as Dave mentioned, I have been working on James Webb for a long time. I think I was on the first science working group in 1998. We realized that it wasn't going to launch for a while. We thought it would launch sooner than it did. But we also realized that a lot of science would happen. Science moves quickly, and some of the most interesting science that it would do is stuff we hadn't thought about. But we felt that if it could make progress in 4 different really big picture areas, then it would have enough capabilities to do a great job on the science of the day when it was launched and operated. So we had these 4 science themes we picked out. Being able to see the first galaxies that formed after the Big Bang. Then to see how these galaxies evolve over time. We think they're much different then. The Big Bang produced just hydrogen and helium, maybe just a little teeny bit of lithium. And the stars are much different then. They're much more heavy elements now that help the stars cool and help star formation in normal galaxies. But somehow stars formed, they formed into galaxies. Then the galaxies evolved over time. It took time to develop spiral structure and whatnot. And we'd like to see how that happens. Also like to understand how stars form and die, so sort of like that infrared picture showed you, how planets form in their disks, and also to understand planetary systems, the near and far, both our solar system and also in other places as well, which we were just getting to know in 1998. The first planets around main sequence stars had just been discovered in 1995. We didn't know whether this telescope could do much with them, but we're lucky because we think it can, which I'll show you in just a bit. So this is going into the 4 science themes a little bit. This first light and the epoch of reionization. So the idea is that the Big Bang was very hot, and the produced it was so hot there was only energy. And as the universe expanded, because we know the universe is expanding from redshifts, we saw the radiation cooled, and then particles actually condensed out of the energy, and that cooled. So after about 300,000 years, the particles cooled enough to about 3,000 degrees, and then atoms could form. And that's where we can see back to theoretically, and that is when we look back at the radiation from the Big Bang, as the cosmic microwave background radiation. And then after maybe a few 100 million years, stars started to form. So stars started to form, and then they started to form galaxies. And this is the area which we hope to see back to. So maybe when the universe is just a few 100 million years old, so that's about 13.5 billion years ago. Then Hubble can see to this period where the universe is about twice as old as we hope James Webb to see. The galaxies have become more evolved, we think. And then present day we see the kind of clusters that we could see in our own telescopes, right? Like Stephan's quintet. And here all the light from the stars have completely reionized the universe. So light has had enough time to travel from the stars that formed and from the ultraviolet radiation ionizing hydrogen again, so we can see and the universe is clear. I mentioned that the universe is expanding. The Big Bang set things in motion. There are also some other events since then, and now dark energy is sort of taking over the expansion of the universe. And so that means any 2 points in the universe are moving away from each other. And the light is also Doppler shifted. So if there's a very distant galaxy across the universe that's putting out light in the visible, it will be Doppler shifted into the infrared. So that's yet another reason why the Webb Space Telescope sees the infrared. If things in the early universe can be expanding so fast that they're approaching the speed of light in the expansion, they can have a Doppler shift of something like 10. So that means that if they're hydrogen alpha lines, we know at 656 nanometers, are going to be shifted out to like 7 microns. So you really need something in the infrared to see that light. And ultraviolet gets shifted into the near infrared. So all these first galaxies that we want to see eventually evolve and become galaxies like the Milky Way. We know that gravity is involved in this, but we'd also like to understand how star formation changes with galaxies through time, how dark matter seeds clusters of galaxies. And if we just look to do a deep field, I think this is a simulation. There are real deep fields, like the Hubble deep fields is similar to this. You'll see galaxies at all sorts of different states of evolution. There'll be a few really faint ones here that are small. Those are the really old ones, some red proto-galaxies that are really redshifted. And we'll see bigger ones that are nearby in more structure. And so we like to be able to use this to piece together how they evolve, be able to measure redshift in deep fields. There are some deep fields being done with James Webb right off the bat. They're going to be much more sensitive than Hubble, and we'll be able to get like hundreds of thousands of objects and be able to trace together evolution between them. And there's been a lot of supporting modeling involved also, so that we can use these data to actually understand the chemical evolution and the dynamical evolution of these galaxies. And this just shows a picture here of what we hope to see in terms of these steps. So the first proto-galaxies, very red because of the red shifts, small. The stars are very different because they're just hydrogen and helium. And then later, they have subsequent generations of star formation. The stars get to be more enriched in heavier elements, and several of these objects start to come together to be more massive. And then you start to get spiral structure after a few billion years, and then you get to things like we have today. So the story goes, and we will see if that is the truth. Now, stars and planets. before Hubble launched, I remember I was actually in grad school in the 80s, and we pretty much knew about disks around stars, but not from pictures. We could measure velocity information. We didn't have resolved images that were good enough. But Hubble, once it launched, it actually did produce images of disks around young stars. If you remember the Proplids images of the trapezium and Orion, and there have been many other images since then, also at other wavelengths. You've probably seen the D-sharp images from ALMA showing these beautiful ring-like structures around young stars and with gaps where we think planets are forming. And so with Webb, we'd like to not only image the disk, but also be able to sample their chemical compositions and also see if there are protoplanets, young planets forming in there. Now, this is an example of young stars in Orion. So this is the visible light image on the left, and this is the infrared image on the right, just sort of like I was showing you earlier. So there's this whole cluster of young stars. This is where the action is, and it's just completely invisible in the visible image. And so this is from VISTA. This is a ground-based, I think, 4-meter telescope in Chile. And we're actually going to be studying a lot of these young stars with Webb, because we can go down to stars that are just about the mass of Jupiter, or a few times the mass of Jupiter. So we want to understand what makes a star, what the numbers of young stars versus time. And it's really good to look at clusters like this, because we know they're all about the same age. And any differences don't have to do with age. They all have similar chemical composition. So if we see a bunch of different masses there, we know that there's a physical process involved. Okay, planetary systems. Let me show you this little graphic, courtesy of the European Southern Observatory. This is how most of the planets are formed, so are found. So we've got about 4,500 known planets. Over 1,000 of them were discovered with the Kepler spacecraft through this technique, this transit technique. You're probably familiar with it, that when a star moves in front of its planet, if we have the right alignment, we'll see the star dim. And that's what this plot is. The star brightness will drop by like 1%. Some of you may have observed transits with your own telescopes. And with James Webb, we're going to use this technique to actually measure molecules in the atmospheres of the planets. We've done a little bit of that with with Hubble, but Webb is going to show us a lot more. And there are also more of these being discovered. So this is sort of the picture about how this happens. So if we're just looking at the star before the planet transits, we disperse the light, we get a spectrum. We see these little lines here due to absorption lines in the star. And then at a later time, so it could just be an hour later, then the planet moves in front of the star. And the light doesn't go through the planet, but it goes through the fringes of the atmosphere. And we'll start to see different absorptions. These other deeper lines here are what's due to the planet. And if you do a difference between those two, you can take the star out and you get just what's due to the planet. So it's a while that this works, but this is transit spectroscopy. And we're doing a lot of this in the first year of Webb. In fact, we're going to be doing 70 planets in the first year of Webb, and that's as many as Hubble has done over its whole lifetime. And we'll be able to look at broader wavelengths, which means a lot more molecules to understand their atmospheres much better. This is an example of the kind of wavelength coverage we can do. This is pretty long wavelengths. This is going from the mid-infrared from about 5 microns out to about 18 or 20 microns. Interestingly, so in our solar system, Mars, Earth, Venus all have strong CO2. Even Mars. Mars doesn't have much of an atmosphere. It's like 100 times less pressure, but CO2 is a really strong absorbent. Earth, as we all know, we're all well too familiar, we're putting more CO2 in the atmosphere all the time. You see the Earth is broader than the Mars one. That's because it's higher pressure atmosphere. And Venus is much higher pressure still. So you see that really broad feature. So we're going to be looking for this around planets. Now, Earth, you see, is different from these other ones. How is Earth not like the others? It has this ozone feature. This is O3. Normally, you wouldn't have O3 because it's not equilibrium. The O would combine with C, and you'd get like CO, or it combine with H, you'd get H2O, and or CO2 or CO2. What is driving this? Well, it's life, it's plants. So O3 is made from O2 that plants make to do the photosynthesis with. And also this is water in the Earth's atmosphere as well. So this is the kind of information we're gonna look for with Webb around other planets. This is one of the systems. What we're gonna look, the TRAPPIST-1 system. This is a wild system, right? You're probably familiar with it. It's about 40 light years, 12-ish parsecs away, 7 planets, all roughly the size and mass of Earth and to Mars-ish size. And this one is C is about Venus temperature, B is a little hotter, D is a lot like Earth. And in the first year, we're going to be looking at all these planets and different techniques to look for different things. I'm going to be trying to look for CO2 in B. And there have been a lot of papers out, people trying to understand whether there should be CO2 there. It could be produced by interactions between the original volatiles, the ocean boiled off, never really had an ocean, and magma, except it may have had a magma ocean, probably did. This shows the TRAPPIST planets in terms of the illumination left to right from the star. So when these on the left are closer to the star. So B is like in between Mercury and Venus. This is the density of the planet. So Earth is up here, D is down here. So with Earth being 1, so it's just a little smaller, a little less massive, very much like the rocky planets in our solar system. And it's a great system for transits because it's a small star and all the planets move in front of the star. All right, so here's where I'd like to, I can stop for a minute and see if there are any burning questions. We'll also take questions at the end.
Okay, let's see.
I have a question.
Go ahead.
Okay, I'm intrigued by by JWST's ability to spectroscopically give us information about exoplanet atmospheres. And I'm wondering, does your ability to do that depend upon the temporal resolution of the instruments? Or is that something that is only a function of how long that planet stays in front of the star?
You bet. So we do need to know the timing. Yeah, spent a lot of time specifying the timing, and there are all these taxes I get charged too if I want the timing too precise. And the timing can change. We have these transit timing variations, particularly these multi-planet systems. It turns out TRAPPIST looks pretty good, but if they're in resonance, yeah, it can be around. So definitely want things to minutes, timing to minutes, and you have to look at these transits, you know, when they're going to happen in advance by looking at them for years. So that is a big deal because that's the only way we know, like when the planet is not in front of the star versus in front of the star. And people have missed with Hubble and Spitzer in the past. So that's important.
Forgive me, just another question and I'll shut up. How fine is the temporal resolution of the instruments that you're working on?
Oh, that's funny. We were just talking about how good the spacecraft time was. And we were told about a second is about the accuracy. We have better resolution. But okay, that's supposedly the accuracy of onboard spacecraft time.
Okay, I'll shut up for now.
Is there another question?
I don't see anything else.
Okay, all right, great.
At the moment, I don't. No.
Okay.
Oh, here, there's actually, I see one here about the universe being symmetrical, looking back towards the Big Bang. Basically, yes, and people have done that. They're like northern and southern fields of deep fields. There's good south and good north. So and in fact, the universe just from the Big Bang radiation is amazingly uniform. And that makes us believe that there was like this inflationary period early on. So that it's only the asymmetries in the Big Bang is only about 1 part in 100,000. And that won a Nobel Prize a number of years ago.
Another quick question, forgive me, and then I'll shut up. So I just want to make sure I understand this. JWST, the Hubble can only go back to 600 million years before the Big Bang, and JWST can get to within 300 million years of the Big Bang. Do I have those numbers correct?
Yeah, that's about right. So James Webb, and I mean, we'll have to see, because we'll have to see the actual redshifts that we get and whatnot, and also what kind of objects there are. We think they're pretty different kinds of objects. So that's why one of the reasons why Hubble peters out.
That's very cool. I'll shut up now.
All right. So now I bet a lot of you are curious about the observatory. So let's talk about that. This doesn't look like our telescopes, does it? So This has been in the news a lot lately. So we've got a segmented mirror, 6.5 meters diameter. And I'll talk a lot more about the mirror segments and materials and sizes and all that. Secondary. And then the light goes through this shroud here, this baffle, and then the instruments are on the back. Now, we do need some kind of baffle. Hubble is all in this big tube, right? But here we've got this deployed sunshade instead. So it gives us continuous night on the telescope side. And it also allows the telescope to cool off. So I'll talk a little more about that later. So this side of the telescope is continuously warm. I'll show you that. And this always points at the Earth. The telescope is at this Sun-Earth L2 position. It's about a million miles. It's almost a million miles away. I think it's going to get to L2. It'll have its injection burn this Friday. And then the telescope side was cooling off. And that's important for an infrared telescope. Show you some more pictures here. This is the telescope with the primary mirror. So it's on its side here. The secondary has been stowed. And this was the launch configuration with the secondary. Here on the right, we see the primary segment wings. So there were two wings here. And this is to get the telescope small enough to fit into the 5-meter rocket ferret. And here we see it with the wing stowed, the secondary stowed with the sunshade deployed. And the sunshade had to be stowed also. I'll show you all that. Relative size between Hubble, monolithic piece of zero door, so like glass. And I'll get into the James Webb materials soon. And so 6.5 meters segmented. Spitzer was 0.85 meters of beryllium. Okay, and here we got pictures of the sun side, the hot side. These structures here where the sunshade was stored in, all this mylar, this Kapton stuff, got pulled out of there, got stretched out of there. That's the solar array. That's a high gain antenna. And then these are booms that actually push the sunshade out. This is a trim flap because you see that there's more sunshade on this side than another. And then this helps balance the solar radiation pressure like a sail. And then already went over most of the components here on the cold side. Okay, so just like our telescopes at home, James Webb is made out of beryllium mirrors that are coated in gold, right? That's what we all have, right? So why beryllium? Why gold? And one thing I will point out is that the mirrors were all polished here in Tinsley. The mirrors made quite a bunch of trips around the country. The beryllium was mined, I think, in Utah. They got pressed into some sort of blank, maybe in Tennessee. Then the blanks got sent out to Tinsley to be polished. And as you know, the telescope has to cool. So they were fabricated warm, but had to be tested cold. They got sent to the Marshall Space Flight Center in Alabama to be tested in a cold chamber. And so that's a lot of trips and a lot of work on all the mirrors. This shows one of the segments, so 1.3 meter segments, only about 20 kilograms for the segment itself, and for the whole assembly with all the stuff that moves it, about 40 kilograms, so less than 100 pounds for one of these 1.3 meter segments. Something tells me that if you've got a 1 meter glass mirror and a mount for it that could help it perform at the diffraction limit, it's going to weigh more than 100 pounds. Don't have a lot of mass capability to get into space. So that's one of the reasons why we use beryllium. Beryllium is 7 times the stiffness to mass as aluminum. And it's really wild. If you ever get a chance to play with a piece of it, it feels a lot more like a ceramic than a metal. But it's a metal. It's got free electrons, but it feels like a dinner plate or something when you put it down, and it polishes nicely. This shows several of the segments being put in this configuration here. This is an optical test chamber. This is where they're taking cold at this Marshall Space Flight Center. And so it looks like they tested about 1, 2, 3, 4, 5, 6 at a time here. So they'd polish them at Tinsley. They'd have an estimate of how the figures would change. Then they would measure them cold, and then they do an optical map of them cold. And then Tinsley would work on them back warm again. This shows the different prescriptions. So, we've got 18 segments in 2 different rings, but there are 3 different prescriptions. All of the A's, the innermost ring, are the same. The B's are sort of like the corner ones, and then C's are closer because just the way the hexagons work. So they're all part of a bigger parabola is the bottom line, and that's why they have the figures they do. And there are other mirrors around too. There's the secondary mirror, there's this fine steering mirror, there's a tertiary mirror as well. This fine steering mirror allows it to do fine compensations with guiding without having to move the whole telescope, because the whole telescope is floppy and you don't want to move all of that mass at once, and it's not going to move well. So it's a lot easier just to move this little mirror at like several hertz or something. Why gold? Well, it has really high reflectivity in the infrared. So it's over 99%. You can see here. So these are the James Webb wavelengths from about here out to there. It's always at least twice as reflective as aluminum out to, let's say, at least 5 microns. And it's a lot more. So it's not so much that we care about the extra light, like getting 99% of the light versus 98% of the light. What we really care about is this other thing called emissivity, which is 1 minus reflectivity. So the more reflective something is, the less it's going to emit in the infrared, because it's totally reflecting. Any kind of incident light that hits it gets reflected back. It's neutral. But if something is emissive, if it's like a few percent emissive, it's got a temperature and it's going to emit infrared radiation. We don't want that, because we want a very cold environment so we can see very faint things in the infrared. We don't want the telescope itself to overwhelm that. Aligning this telescope is going to be fun. So I think it's scheduled to start around February 1st. I'm going to be there at the Mission Operations Center. So we're going to turn the camera on once it gets cold enough, which I think is going to be on the 28th, the near-infrared camera. And we're going to look for images. So hopefully we'll initially see 18 images, 1 from each segment, but it's probably not all going to be in the field. Some of these segments, because they were, they were put in this mechanically locked position. I'll show you some more about where the segments are, and they have to be made into a mirror. So we first have to like tip and tilt them all so we see the individual images, and then we do a focus with the secondary, and then we can also focus each segment separately, and then we start to combine them. You start to stack them, and then you start to phase them, because then you start to actually look at the edges with this arrangement. We have these little grisms that go across each segment boundary, and then we can use as an interferometer, and then we make sure that the 2 edges line up, and we get all, and that's what this thing here is, this dispersed Hartmann sensor, and we get everything working as one telescope. And this kind of shows the Wiffle tree arrangement for each segment. They can piston, tip, and tilt. So hopefully then we'll get a telescope working, and this is going to take over a month. And just to get the first alignment, and then we're going to transfer it to other instruments, go from hot to cold, whatnot. We're going to monitor it as there are going to be different temperature gradients across the telescopes. We're going to monitor how the point spread function changes with different attitudes. This is a comparison of James Webb versus ground-based telescope, Keck. NASA has an interest in Keck. I'm sure you've probably heard about Keck. And I'm actually a NASA rep for Keck. I've used it a fair bit. So Keck is bigger, 10 meters. It has 2 10-meter telescopes. That'd be nice if we had 2 10-meter telescopes in space. So each one's got about 3 times the area of James Webb. James Webb is faster. F1.25 is the primary mirror, and F1.75 for Keck. Being fast here allows these telescopes to be short, which allows them to allows James Webb to fit into his rocket, but also less massive structures. And before you going, holy cow, how could you figure a 10-meter mirror at 1.75 or 6.5 meter at 1.25? Remember that you're figuring all the segments separately. And so there are about 5 segments across James Webb. So each segment's only about f6. And together they work as about f1.25. different wavelength ranges. So there are 18 segments on James Webb. There are twice as many in Keck, and the Keck ones are therefore a little bigger because it's got 3 times the area. Mass here. So again, we saw that the blank itself is 20 kilograms for James Webb. So that's less than 50 pounds for just the beryllium segment. Wow. 400 kilograms. So that's almost 1,000 pounds for Keck. The whole telescope, James Webb, is 6.2 tons with fuel. And just the rotating part sitting on the azimuth bearing of Keck is 270 tons. And James Webb is more expensive to operate if you take the cost of the observatory, amortize it, and over its operating period. I think this is just over 10 years. We might actually get 20 years, so this cost could come down versus Keck. But because we're observing 24/7 or close to 24/7 and not have to deal with day, night, and weather, the difference in cost is not as big as you might guess. All right, so I'll talk about science instruments next. Actually, at the risk of, I'll take, if there are a couple questions now about the telescope, I'll take a couple now, if there are any particularly burning ones.
I have a burning one. How do you slew the telescope?
Yeah, so reaction wheels. So we've got these momentum wheels. So it takes advantage of Newton's second law, right? So that you spin a wheel one direction and then the telescope moves the other direction. And we try to balance pointing so that, so if you spin, so you have like no net direction, but that will eventually you do build up spin on these wheels, and you have to offload the spin, and that's what uses fuel, because you'll actually have to fire a thruster that turns the telescope in one direction, and then you spin the wheel in the opposite direction to get its speed down. All right. So are there, yeah, so maybe since it's a telescope question here, I will see this. Can you talk about how much the fine figure can change the prescription of each segment? So the segments move in piston sort of certainly fractions of microns. So, so 100 nanometers or less, I think, is piston. So we will be able to make it diffraction limited. So lambda at 2 microns. So we're talking about for peak to peak, say RMS lambda, 2 microns divided by 10. So that's 0.2 microns RMS. So the RMS errors of all the mirrors would be less than 0.2 microns or 200 nanometers. I missed a question here about, so there's a question about solar sail. Let's see. No, the reason why we have this solar tab is to minimize any kind of imbalance. So we don't think that solar pressure is going to cause burns of fuel. And then there was a question about combination of absorption lines found in exoplanet atmospheres cause the hairs in the back of your neck. Well, I can't speculate on that, but there are a lot of fine lines in there. In order to see these fine lines, we need instruments. So I'm going to move on to instruments now. And we've got 4 instruments on James Webb. So the upper ones do imaging, take pictures. So we've 3 of them will do images. The near-infrared camera, naturally. Near-infrared imaging, the spectrograph, which is kind of like half the near-infrared camera and has some other tricks in its sleeve, and the mid-infrared instrument. So you see these near-infrared instruments go from 0.6 microns, which is where the detectors start working, so like 600 nanometers, just shortward of H alpha, and out to about 5 microns. And then the mid-infrared instrument is 5 microns out to 28. And for spectroscopy, for taking the light and dividing it up into constituent colors, all 4 instruments work there. This near-infrared spectrograph is particularly capable. It's a European instrument. NIRISS is a Canadian instrument. It'll do slitless spectroscopy. NIRCam does slitless spectroscopy. That was one of my contributions to NIRCam. And we're using that for exoplanets. And MIRI does spectroscopy as well. It's a spectroscopy machine. I think well over 70% of its time in the first year is all spectroscopy. This sort of shows the fields of view of the instruments. So again, a familiar object, M51, a few arc minutes. So NIRSpec, I think, is about 3 arc minutes on a side. And these other ones are, NIRCam is 2.2 by 2.2, and it's a very redundant instrument. There are 2 of them. MIRI is about 2 arc minutes by a little over 1, and NIRIS is about 2 by 2. That's not how they're laid out, though, in the sky. This is how they're laid out in the sky. The telescope is a 3-mirror anastigmat. So the tertiary is part of the prescription, too. It's a primary, secondary, tertiary, gives it a wide field of view with good optical performance. NIRCam is close to the center of it. It's going to be like up here. This is the central obstruction. And this sort of shows the fields where all the instruments are. So you can't look at the same object with all the instruments at the same time, but you can look at the same general area. And because the way it works, if you look at some part of the sky 6 months later, it'll be flipped on there. So you can look at NIRCam and MIRI at one time, and then 6 months later, you'll have the opposite instruments on the same objects. This shows where the spectra will be for the near-infrared spectrograph that has several modes here. I'll talk a little more about it, but it has little slits for objects. And it also has this micro shutter array. So if you put, if there are objects falling here, you can open up a little shutter and you'll get a spectrum of the object. And NIRCam, the way this crosses here is that we've got 10 detectors. So we have 2 different plate scales, and there's dichroic. So we can look at short and long wavelengths at the same time. Short wavelengths are sampled with 32 milliarc-second pixels, and we've got 4 detectors over the field there. And the long one, we've got another detector that's just right on top of this, and then it's sampled 64 milliarc-second pixels. And this is MIRIS with its slitless spectra. And MIRI over here has these coronagraphs for blotting out a star, so you can see faint planets and other things nearby. This shows the shortwave detector array in NIRCam. This is these 4 of these Mercad telluride detectors made by Rockwell. And so we've got 10 total. So we've got 2 identical channels on, so 2 short waves and 2 long waves. The short waves have 4, long waves have 1. You can see the 2 benches here. So we've got 2 nearly identical systems. You see this is the beryllium bench, this gray thing here. And then we've got the optical components on top of the bench, and the same thing down here. And they're just put together back to back and then put into the instrument module on these rods there. This I don't think is flight. There's a separate set of flight rods. And this was made at Lockheed Martin in Palo Alto. And the leader of it and who designed it is the University of Arizona, with Marcia Ricci there being the principal investigator. This is the near-infrared spectrographs provided by Europe. You can see this is the carousel that all the gratings are on, if you can see that, where they're reflecting. There's also a prism there with a mirror behind it. And its bench, I mentioned NIRCam was made out of beryllium. Its bench here is made out of silicon carbide. So it's another stiff, lightweight material that does well at low temperatures. Then it has 3 different spectral resolutions. And I kind of mentioned it's got this micro shutter array, so we can do spectra of multiple objects, which is pretty cool. And it also has fixed slits that we'll use for planets. And it has this integral field unit where you can get it's about 3 by 3 arc seconds, where we could get a spectrum of, sorry, the integral field is here. Yeah, 3 by 3 arc seconds. You get a spectrum of every point in that. This shows how this micro shutter array works. So it's about 90 microns across here. And so it's fabricated with microelectronics techniques at the NASA Goddard Space Flight Center. When you image a field onto the array here, you see that this array of shutters, and you can choose which shutters to open up to get spectra of the objects that you want. And you can't just leave them all open, because then all the spectra overlap, and it'll be hard to figure out what is what. Although we do that in some modes for brighter objects. This is the mid-infrared instrument here. And oh, sorry, this is NIRIS here. Yeah, it's a Canadian instrument. So this is made out of aluminum. And it's almost like one of the channels of NIRCam, like the long wave channel. So 2.2 by 2.2 field of view. And it does slitless spectroscopy. It's got this nice transit mode. So it'll go from 0.6 to 2.5 microns. That'll be really used to clean up a lot of these exoplanets. And it has this high resolution mode, this aperture mask interferometry, where you can use the full, it's the highest resolution mode on the observatory, and the spectroscopy. Mid-infrared instrument was put together by a consortium of 10 countries. It was in the Europe and split with the US. I'm on the US side of this. And it also has imaging, integral field spectroscopy. That's where you get a spectrum of every point in a small area of a few arc seconds. And also single object spectroscopy. Then it has a number of filters and these coronagraphs, so we can look for planets around stars. The telescope here is getting put together at Goddard. And this shows the instruments here, all in the instrument module. And how the instrument module then is configured to go onto the back of the telescope. There's a radiator off here that's been deployed. This is the telescope with the sunshade put together at Northrop Grumman, again with the wings back on the primary and the secondary stowed. The sunshade layers, it needs 5 layers here for various reasons. The biggest of which is because it's really hot on the day side. It can be like 50 degrees C, so over 100 degrees Fahrenheit. But we want it the backside to be cool because we want the telescope to cool off to about 40 Kelvin. So that's almost minus 400 F or minus 230 C. So that's well over 200 degrees C or 450 degree F temperature gradient on the 2 sides of the sunshade. The yellow stuff is all ground support equipment. This is the sunshade is folded up into these things called unitized pallet structures, a pretty useless acronym for describing what's in there, but they hold the sunshade, they held the sunshade. And this is just helping to fold or unfold all around the telescope to get into the launch configuration, which is what you see here with all this folded up. And this is at Northrop Grumman down in Redondo Beach. And hopefully you understand a little better now what makes this telescope, why it looks so funny. So a lot of people have worked on Webb. So over 1,000 people, mostly in the US and Europe and Canada, have worked on Webb. Also some collaborators in Hawaii. And it was, went over Europe provided some instruments, provided the Orion launch. US built a lot of stuff, mirrors, instruments, whatnot. And it launched here from Kourou in French Guiana. And even more people will use it and benefit from it than the thousands who built it. So early on, I talked about some of the science that we thought it would likely do and have capabilities. And this is what it will do in the first year. So this is what came in for the first years with the proposals for Webb. About 25% of the time requested was for exoplanets and disks around young stars. Then about 25% of the time is stars themselves. So this is the physics of individual stars. This is studying structures of stars. 26% of the time on galaxies. So this is just like kind of the 4 themes. It's just amazing how this worked out. And then these are all sort of like early universe. So cosmology and supermassive black holes, and also some solar system observations. So believe it or not, I think we picked the right capabilities. This shows where it is in the Sun-Earth system. It is not to scale. So L2 is about 1% of the Sun-Earth distance on the other side of the Earth here. And L1 is about 1% of the distance here. So these are stable Lagrange points in the Earth-Sun system. It's easy to understand some of these more than others. Like L1 is where gravity kind of balances right between Earth and Sun. L2, there's also a moderately stable point, but it does have to do station keeping there. And L3, 4, 5, these are stable points. And like for Jupiter, those are, I think, where the Trojan asteroids are. This shows what it looked like in the fairing, all folded up there when it was launched on Christmas Day, bright and early on Christmas Day. This is a picture of the launch. It went really well. It launched right at the beginning of the window. I couldn't believe it. That never happens. And it really did go well because I was listening to the live NASA feed. I was also listening to the control room to see if there are any whoopses in their work. It went well. This is the last pictures we have. So this is from the upper stage of the Orion 5, right after it ejected James Webb, the little spring actuator, let it go. This is the telescope moving away. And then like the last image we got was the solar array deployed, which is really cool. I don't think people really expected to be able to get that. This is all the deployments that it went through in the first 2 weeks that were completed by last Saturday. Yeah, that's when I think we got the last mirror segment. So after first thing is that solar panel, that was like at launch plus 30 minutes. We had to get power on it. And then after about 2 days, these pallets came down. And after several days after that, the sunshades booms went out. And then it took a few days to separate the layers. And so we're talking about like, it was about a week here. And then the secondary came down after about 12 days. And then the mirror segments. So I think this is day 13, day 14. And also the other thing that had to happen, I don't know if you can see here, but the telescope actually pops up a bit above the sunshade. This is this deployable tower. So this sort of shows where it all happened here. So it's slowing down as it's getting out towards L2 because of gravity, basically. And and I don't know if this is quite to scale or not, but I don't think it is. I've got another graph on that. And then at launch plus 28 days, which is going to be this Friday, is when it gets inserted into this orbit around this L2 point. So we did have a really good burn here. This is at this launch plus 12 hours, there's this burn. And we knew we had to have it because we wanted to under boost the observatory with the rocket, and then do a fine control on its speed with a fuel burn here, because usually you just kind of give a nominal amount of boost, and if something is going too slow, you fire a rocket to move it in the same direction. If it's too fast, you turn it around, you fire the rocket to move in the other direction. But we can't turn it around because we can't have sun on the telescope. So we had to do it this way, and it worked really well. We might have 20 years of fuel left. So this is what's happening now. So the deployments are done. Now we're in this cooling phase. This is the first month. And then we got 5 months to check out the telescope and the science instruments. And this is where that month or two of the telescope alignment happens. And then we have to go through all the modes of the instruments to make sure that they're going to do the science that we expect them to do. We've got all these tests planned. There's this kind of a cool tool. I don't know if you've seen it. It's called Where is Webb? And this is the URL here. So if you just go to web.nasa.gov, and that's the big deal, and you get the screen here. It's one of the things. So this, I think I took yesterday. It was at launch of a launch plus 20 days. It shows you the speed. It's come down in speed by about a factor of 3. So 0.3 kilometers a second. The hot side, these are 2 temperature probes on the hot side, up to 50 C. On the cold side, it's getting quite cold. And this sort of shows where you are in the launch deployment and where you are in the deployment sequence and whatnot. And this is the L2 insertion at day, actually it says 28, 29 there. I took this morning. I thought you may want to know how it's doing. So this is the temperatures, the different mirror segments. So they're getting pretty cold, right? It says 81 Kelvin, that's almost minus 200 C, because 200 and because 0 Kelvin is minus 273 C. And the secondary is the coldest because it's sitting way out there and doesn't have, it's the furthest from the sunshade. And also you may have read, and there's a blog, blogs.nasa.gov web, the URL was on the other page. We've been moving the mirrors because they were in the stowed launch configuration against these hard stops to protect them mechanically. And they just have single, their pistons are just these screws. And they're being moved off their hard stop. So they're being moved out to half an inch, 12.5 millimeters. And see some of these, if you can read that, are already at half an inch. Most of these are around 8 millimeters away off their pads. And that was from this morning. I thought I'd just end here with a point about how we're all going to benefit from Webb. So people have been asking some big questions for at least all of recorded history, probably a lot longer than that. We wanted to know what's in the universe, how old is it, how do we get here, are we alone? And we're going to address that scientifically, try to go through that with some of the science themes. So by seeing the first galaxies that formed, we'll learn how they evolved into ones like the Milky Way. So that's kind of like how do we get here? We'll see how stars and planets form and die. So that's what's in the universe. And we'll learn about whether planets and other stars, how they're like and unlike Earth, and whether any of their atmospheres could be hospitable for life. So hope that satisfies a lot of people. I think that a lot of this stuff is, it's almost, this fundamental research is almost more like art in terms of how it just impacts how we think about ourselves. More practically, it has really helped us advance some scientific technology. People in Mountain View, Bay Area, California, all over the world have helped build the Webb. It's the most complex space telescope. A lot of technology development has benefited ground-based observatories like these mercury, cadmium, tellurium arrays. Had an early prototype of this slit mechanism on the spectrograph we actually used in an instrument at Keck. And again, Webb has brought thousands of people together building it, and hopefully, its results are going to bring together more. So that's what I have. And thank you for putting up with me, and I'm happy to answer any questions.
Wow.
We have a bunch of new questions that popped up in the last section here. The first one from Bill Evanson. Do you expect the universe to be symmetrical looking back toward the Big Bang? That is, will observations be the same looking 180 degrees in opposite directions?
Yeah, I tried to answer that earlier, but the answer is yes, it does. We've already seen that from the goods fields with Hubble. There's a north one and a south one, and you don't see the same objects, but you see the same kinds of objects. In fact, from the Big Bang observations, it took a long time. The Big Bang looked really uniform. People didn't understand it. And it took this spacecraft COBE to find out. And I think Smoot at Berkeley got a Nobel Prize along with John Mather at NASA Goddard for actually making the first discovery that the universe is so uniform in all directions in terms of the microwave backgrounds. And you're really looking at the early parts. It's uniform to 1 part in 100,000. So that's pretty amazing.
Great, thank you. Yeah, and I see that you did get to that one earlier. Thank you. Make sure this wasn't covered. About the instruments, what are the typical pixel sizes of the detectors in microns, not arc seconds?
Yeah, so the near-infrared instruments have 18 micron pixels. And these are not like your CCDs or MOS detectors. They have to work in the infrared, but the readouts are in silicon. So you have, for the way both these, and the mid-infrared instrument's a little bigger, it's 25 micron pixels. And you also want the pixels to be at least the wavelength of the light. Otherwise, you get this weird diffraction stuff because it doesn't make sense to have a pixel that's smaller than the wavelength of the light. The way these have to work is there's infrared sensitive material, and every pixel of that is bonded with a bump of indium, which conducts to a readout pixel. So it's kind of like a CMOS detector that's been bump bonded to something that's infrared sensitive.
That's interesting. Thank you. Bob Garfinkel asked about on some of the base assumptions here, and what's the easiest way to understand how we know that the universe is only 13 billion years old?
Yeah, that's a good question. So I knew that at one time, but I would guess that it has to do with we don't see stars older than that, right? We know about stellar evolution. And so globular clusters are old, but they're not older than that. And we know how fast things are. We know from the Hubble constant of how many kilometers per second per megaparsec things are moving away. So we get some idea of things that are really high redshift. But emitted their light like over 13 billion years ago. So a few of these things stack up.
Yep. Thank you. All right. Anyone else? You got one last chance to put in a question. Dave, if you have any
Yes.
that you've thought of.
What are
Go
the
for it.
what are the consumable limitations? Which consumables are you worried about running out of? And has there been given any thought to sending up something to try to refuel it or supply more consumables after 10 or 20 years?
Yeah, that question.
Sorry.
So we were pretty worried about fuel. So I'll keep my share up just in case there are any other questions about other things I can show. But we're pretty worried about fuel because the telescope was really only required to operate for 5 years of fuel. We had a lot of margin. We thought we could do for more than 10, but it depended on how well it could do this burn. The Ariane 5 is such a precision launch. We didn't have to burn that first course correction very much. So we think we've got over 20 years of fuel. That really is the only consumable. Now, that said, things have finite lifetimes, and it gets really expensive to build things that last a really long time. And like Hubble has had numerous gyroscopes repaired, it's had instruments replaced and all this. And the things were designed to last at least 10 years. And hopefully it'll last longer than that. And there are a bunch of smart people will figure out how to get more life out of this. Going there. Well, we don't have anything that can go there. At one point, yeah, there's people at Goddard, NASA Goddard Space Flight Center were really interested in doing robotic servicing of the Hubble and other stuff. And we actually got put on basically a grappling hook, this little fixture that could be grabbed, but you really don't want to go anywhere near it in a spacecraft, because a spacecraft that's going to get near it has thrusters, and it's going to be spewing stuff out. If there's a person going to come out, there's going to be an airlock. It's going to release air, and water is in the air, and you've got this really cold telescope. All this stuff is going to freeze onto the telescope and kind of contaminate it. So we don't want that. And it's not really built to be serviced. Hubble was a lot more built for big bolts and simple and all that. It's hard to get inside of this thing. And it's probably not something you want to do a million miles from home.
Speaking of consumables, can a mid-infrared instrument still be used at reduced performance in some way after the liquid helium becomes exhausted?
We don't use liquid helium. So the Spitzer spacecraft, it had, I think it was helium. It wasn't hydrogen. It was a helium cryostat, and the boil-off cooled the telescope, and it had a limited time. We have this kind of cool technology, a closed cycle cooler. So there's a pulse tube and a Joule Thomson. And these do not have cryogens. They they do, but they're in this loop. So like helium is circulated in this loop as a liquid, and then it expands and cools, and then it gets recompressed. So it's using electricity to form a cooling loop, kind of like your refrigerator.
Yeah.
And so if it doesn't leak, and we don't think it will, we shouldn't run out of coldness. Eventually, detectors get torn up by cosmic rays. This is not in Earth orbit, so you don't have the protection of the Earth's magnetic fields for cosmic rays. But the good news is that these detectors are pretty tough. There's mostly silicon, and silicon take a fair bit of radiation.
That's interesting. I have a question. After the incident in Guyana, when there was that loud thunk, and everybody was worried about whether any damage had been done, how far into the instrumentation were they able to go to assess whether there was any damage? So, for instance, do we know that the micro slits work properly after there was a high degree of shock?
That's a great question. There was mostly an analysis done for the instruments. They weren't, we really couldn't get into them. So it was I think looking at some things that were accessible on the spacecraft, and then from that trying to figure out how much shock there was, how it propagated. So that was done by analysis. There's a little bit of concern about some of maybe about a little bit of shock given to the cooler that for the mid-infrared instrument. And then the plan there is to not operate it quite as hard as we had planned to get things cold. So just take a little more time. But we think that is, we think that actually that shock was not a big deal compared to what it got during launch.
All right. Well, thank you. How did somebody asked, how did it feel the day of the launch after 25 years of work to see it actually take flight?
It's about time.
Right.
No, I was really happy. I was really happy to see the launch
bet.
go so well. You know, it's like we had we've been doing a lot of rehearsals for operations and rehearsing the launch. We're using these simulators, and everything has just been not working well in the simulations. But it's, I think, mostly because the simulators aren't very good. And it was just such a treat to see the launch go off so well, and the spacecraft work so well, and hopefully the instruments will work so well too.
All right. Well, we hope for the best. All right. Well, thank you very much. This was a great talk. I got nothing but accolades from both our Facebook viewers and our Zoom viewers tonight. And we wish you the best of luck. And we'll be following this very closely.
Great. And if I could just answer one more question here.
Sure,
this is
go.
one thing I do know about ozone and the atmosphere of a planet. Very strong argument for life. Yes. And then any plausible arguments against that view? That's a great question, and it's an important one. There are abiotic sources of oxygen. That is important. I think that so, you know, the ozone is created from O2 getting broken apart and forming O3. That's what ozone is. For example, there was probably for a while abiotic ozone on Venus. If you have water, and if you go through a runaway greenhouse, which we don't want our planet to do, the water, all the oceans can boil off and produce a bunch of oxygen. The hydrogen escapes, and you got all this oxygen there. So you can have abiotic oxygen, and there are different ways of getting abiotic oxygen too, and that can form ozone. So they're good ways and bad ways, and people are working on all sorts of tests for habitability that way. You know, to say like, well, you probably want some methane there too from and CO2 and all this stuff, at least from life as we know it, along with the oxygen.
Okay. Well, I guess that's it. Thank you all very much. And Dave, enjoy the rest of your weekend, and you too, Thomas. And we'll talk with you later.
Thank you. And thanks for having me.
You're very welcome.
Bye.